Well, good evening, AIAA. So my name is Chris Crumley. I'm chair of the AIAA Public Policy Committee, and we're here for the Durand Lecture for Public Service, which emphasizes notable achievements by a scientific or technical leader whose contributions have led directly to the understanding and application of the science and technology of aeronautics and astronautics for the betterment of humanity. This premier lecture is in honor of Dr. William Durand, who was a U.S. naval officer and a pioneer in mechanical engineering. During Dr. Durand's remarkable 99-year life, he contributed significantly to the development of aircraft propellers. He was the first civilian chair of the National Advisory Council for Aeronautics, or NACA, the forerunner of NASA. The Institute's Public Policy Committee takes pride in selecting accomplished leaders in aeronautics and astronautics who can share their knowledge through the Durand Lecture. It's my distinct honor to introduce you to the winner of the 2023 Durand Lecture for Public Service, my good friend, Dr. Wesley Harris. Sometimes you discover a mentor just by virtue of a relationship. So young people, take note and keep your relationships as you work through your career, especially here in AIAA. I was introduced to Wes by his first graduate student, Dr. Woodrow Whitlow of NASA, that I worked very closely with. Let me share just a little bit of the biography of Dr. Wes Harris. He is currently the Charles Stark Draper Professor of Aeronautics and Astronautics at MIT, Massachusetts Institute of Technology. He's also head of the Newhouse Residence Hall. Now, why would I say that in his biography? It gives him a chance to mentor other young, fresh minds. And as a matter of fact, I ran into a young man who worked for Blue Origin a few years ago. He was from MIT. I said, "Do you know Wes Harris?" He said, "Yes." He said, "One time I did not have the resources to go home at Thanksgiving, and I was going to stay there in the dorm. Dr. Harris and his wife welcomed me and had Thanksgiving dinner at the Harris home." So he just is always giving back. From 2003 to 2008, he served as MIT's head of the Department of Aeronautics and Astronautics, previously held several faculty and administration positions at MIT. His research area, unsteady aerodynamics, aeroacoustics, rarefied gas dynamics, sustainment of capital assets, hypersonics, and chaos in sickle cell disease. He's credited with more than 130 technical papers. He has served as the NASA Associate Administrator for Aeronautics from 93 to 95. Prior to that, he was with the University of Tennessee Space Institute in Tullahoma. He was with the University of Connecticut from 85 until 90. He received his Bachelor of Science degree with honors in aerospace engineering from the University of Virginia, his PhD in aerospace and mechanical science from Princeton University, many, many, many honors. Even last year, he was named an honorary fellow of AIAA. He's a member of the National Academy of Engineering and was elected vice president of that academy in 2022. Dr. Harris will be speaking on a half-century of research in fluid dynamics. Now, please join me in welcoming our distinguished lecturer to present the 2023 Durand Lecture for Public Service, Dr. Wesley Harris. Thank you, sir.
Thank you much. Good evening, friends, colleagues, AIAA family. I would like to start by offering my humble, sincere thanks to our organization, to the AIAA, its leadership, the Public Service Committee, those who nominated me and supported me and toward this particular honor. Those of you who are close enough will see a strange-looking attachment on my left lapel. It's a sign of age, not achievement, unless age is an achievement, and perhaps it is. It's different in the sense that it is a rocking chair. And folks who've been around since the age of dirt eventually land in a rocking chair. But that gives me an opportunity to speak to you in a more relaxed manner, to talk about how Wes Harris arrived here? What are the steps that are so important in that process? So as we talk about a half century of research in fluid dynamics, I'm going to talk about people as well. I'm going to talk about mentors, teachers, supporters, graduate students at the University of Virginia, graduate students at MIT. I'm going to talk about fluids, Navier-Stokes, diffusion, real gases. I'm going to talk about tools that we're fortunate enough to identify and use to solve some of our problems, experimental facilities, computational tools, analyses. And we're going to talk about some of the physical modeling as we walk our way through a range of Mach number, a range of Reynolds number, a range of Newton numbers, and a whole host of other parameters over the 50 years. But the bottom line, the get off stage comment, is going to be about people. It's going to be about people. So Chris, Ryan, and Patricia, and Monica, and the group, thank you for this opportunity to share some experiences with you. Okay, so I'm trying to get the first chart. There we go. So, MIT folks are always nervous, and because we don't really know much, we're always giving quizzes. So, the gentleman on the right is young and is known. The gentleman on the gentleman on the left is known. The gentleman on the right is very old and is attempting to climb into an airplane. So, given Top Gun Maverick, what is the relationship between the people photographed or pictured there as well as the photos themselves? And we'll try to have an answer to that as we get further into our conversation. So this is what I want to walk through. Some introductory comments, which I will continue in a moment, but I want to talk about shock structure and gas mixtures. What's the problem we were trying to solve? What tools did we use to solve that problem? Did we put it to bed? Has there ever been another publication on that area? I want to talk about sonic booms. Growing up around Wally Hayes, sonic booms were always a part of the conversation. What we did not treat, what we didn't understand, of course, in those classroom discussions, is what happens to the sonic boom in a gradient field. Then I want to waltz a little bit with the aftermath of the Vietnam conflict and talk about helicopter rotoacoustics. And that's really the essential part of the corpus of work. That's where most of the graduate students that I had the great fortune of working with landed. To be honest with you, truthful, I don't think I would have earned tenure at MIT without those students in that helicopter rotoacoustics group. We ricochet a bit further to unsteady, nonlinear transonics, and then I lost my way and asked some questions about blood flow. Two particular problems, two particular PhDs in blood flow I would like to talk about and have some conversation. And then the get off stage area is hypersonics, where now we have a group of 9 students in our hypersonics research laboratory exclusively doing aerothermodynamics. We don't do materials, we don't do GNC, We don't do energetics. We are fairly strongly committed to aerothermodynamics. And then to introduce my students by name, of course, and then to have some final comments to offer. So that's a wash in words and a chart that deals with technology, with research topics. But the other plot, the other theme that I want to express, to get across today, is that about people. So what about these people? In high school, a woman named Eloise Bowes Washington saw something in me that I don't think anyone else did. So in my junior year in high school, we built a cloud chamber to investigate the collision of amphiparticles with water droplets. Now, this was in the 50s. There was no internet. There was no model that you could go to, look up and get your measurements and get the pieces together. But we built the cloud chamber, and the cloud chamber was the start of my curiosity, but also the guidance, the firm guidance from Eloise Bowes Washington of what is this thing called scholarship. How does one generate knowledge, and why? That experience propelled me to go to the University of Virginia, and there I met two people that have had a profound impact on my life, and that's really the pillars of the department in those days, George B. Matthews and John E. Scott. Both earned their PhDs at Princeton, and they made sure that if I graduated from UVA, I had only one option for graduate school, and that was Princeton. That turned out to be a blessing. The other person that has had a profound impact on Wes Harris is George K. Bienkowski. He was my PhD thesis advisor. So Washington, Matthews, Scott, and Bienkowski. Informed me as to what scholarship is about and why, and slapped me very hard so I would not forget. And the takeaway was not the cloud chamber, was not the gas mixture and shock waves. The more fundamental idea of how to identify and present a well-posed problem. How to pick, how to discern, how to identify the critical questions that must be resolved in order to solve that well-posed problem based on an hypothesis. How does one select the tools to go about answering those questions? And how do you sum that up with some assessment of the quality of your work? And that was hammered into me, especially by Bienkowski. So this wandering through fluid dynamics, from hypersonics to blood flows, George Bienkowski would be quite pleased to know that I have made such an attempt. So that's the architecture, the tools, being aware, as we all are, tools are constantly evolving. As a graduate student, we barely had computers. We had add-in machines, but I remember the long, big boxes of cards that I would take over to the IBM Center for processing, and hopefully not one of the cards was incorrectly punched Otherwise, a whole day is lost. They also said to me, Wes, go for hard problems, meaningful problems where there is value. But do so with intensity, with a fire in your belly. Otherwise, it's not going to be fun. So these people set the stage, which allowed me to move into a world where I would have an opportunity to do what they have done for me, to serve as a true mentor, to continue to understand what it means to be a steward of the discipline, and to make sure that those ideas don't die, that they are passed on to additional students. So that's the foundation. Shockwaves. So this body of work came about before humans were landed on the moon. But there was ample discussion around the country on how to probe planetary atmospheres. And Rick Sherman, Professor Sherman at the University of California, Berkeley, performed some experiments in a low-density wind tunnel, a mixture of argon and helium. And he performed certain measurements. And he actually concluded from his measurements that there was a stagnation pressure increase within the shock wave. These are high Newton, large Newton numbers that exceeded the initial stagnation. So how could that happen in the shock wave? We all have knowledge of what one-dimensional normal shock waves, the energy is conserved. T0 is not changing. It certainly doesn't increase. So we ask ourselves, how could we, in fact, unpack this? How could we know what's going on? Because you see, if we don't get it right, then all the measurements into an atmosphere could be wrong, give the wrong interpretation. So what we did was to be careful of the parameters, Mach number, Newton number, Reynolds number, a ratio of masses of the gas, number density of the gases as well. So we did what one would normally do, the conservation of mass of each species, momentum and energy of the mixture, and equally important, to transfer momentum and energy between the competing or components within the gas mixture. We also was concerned about the stress moment of each species and the heat flux. So this problem, once you have large mass ratios and disparate number densities, comes down to a singular perturbation problem. And when we unpacked this, we discovered 5 different shock waves, some with an acceleration of velocity, not a decrease in velocity, but an actual acceleration of the light gas in the shock wave, not the heavy gas. And we observe an increase in a temperature we call the parallel temperature, which exceeded stagnation. And it was dependent not only on those parameters of mass ratio, density ratio, and Mach number, but also on the model of the heat flux, 0, Fourier, grad 13 moment. We examined all of those in order to draw our conclusions. So we're very pleased with what we were able to do, to show, and the Mott-Smith distribution, Saravich's model, all of those had some correct features, but it was our two-temperature model that brought out all of the subtleties of shock waves and gas mixtures, including this so-called anomaly with this stagnation temperature. Okay, sonic booms. The pressure peak on the end wave, that increase, that annoying crack that you hear. You know, one can analyze that to the nth degree and come out with some really interesting results. We know, for example, that peak is a function of distance from the source to the 3/4 power, to the minus 3/4 power, decreasing. The body shape is critically important, and the Mach number. And the Mach number dependency is a rather complex one, including the square root of m squared minus 1 to the 1/2 power again. So it's to the 1/4 power. That's simple enough to do. That's in a very quiet atmosphere. The question we ask is what happens if the sonic boom is moving through a field where there is a gradient? We ask ourselves, what can we measure? Can we develop an experiment, a flow field, where we know what the gradients are and propagate the shock wave through it? So what we did was put an equivalent body of revolution into a Pranomeyer fan. So we could control the incoming Mach number as well as the distance from the origin of the Pranomeyer fan. So we had a good, solid definition of the gradients in the flow field, comparable to what happens when a sonic boom propagates upward as opposed to downward. And we're able to, again, make those measurements optically and physically with pressure distributions or pressure gauges. And we're able to show the variation in the local sonic boom strength in that particular gradient field. Not a universal answer, but certainly we'd have a better handle on what happens to a shock wave, a sonic boom in a gradient field. So right now we're still at very high Mach numbers. You know, this probe going into a planetary atmosphere, and now we have sonic booms. Then the fun starts. There's the Vietnam conflict. And the photograph on the upper left, you see a line of U.S. rotorcraft assets. Some are on the ground and some are above. A close look at those rotorcraft convince you that they are two-bladed. And like our friends from Moscow, we have assets on the ground. Why have your equipment so stored? Very important chart, I think. Why, what, and how did this happen? The other two or other three charts give you a closer view of two-bladed helicopters and some tandem helicopters. Those beasts were noisy, difficult to maintain, and very, very friendly to the bad guys. Very, very friendly to the bad guys. The bad guys could knock one of those out with a .38 pistol. Did not need a missile. In fact, they didn't even need any electronics at all. Those assets were so noisy that the bad guys could just quietly sit back and listen and know which direction they were coming and what type of asset was approaching. So we were asked to take a look at that problem. And the idea is to reduce that noise, but with a constraint that we want to maintain performance. Now, you can reduce the noise by stopping the rotors, but then you don't have a device. So clearly, reducing speed, that's not the answer that we wanted. This obviously was an issue of great importance to the Department of Defense, and it still is. It's also, in our time, of great interest because of urban air mobility, in which most likely there will be complex rotorcraft configurations. And what are the noise profiles that one can anticipate from there? So the problem that we wanted to finally formulate was one in which we were convinced that was unsteady aerodynamics, nonlinear rotor control, noise sources, and propagation, leading us to blade geometry and number of blade configurations as a response to the challenge. We did several things. Out of that came the advanced blade design, novel unsteady pressure measurements, and there's a gentleman here in the audience, that played a major role in that. And I'll get to that in a millisecond. And novel flow visualization. I'd just like to say that the world did not know low-frequency broadband noise exists until we demonstrated that in our laboratory at MIT in our aeronautics wind tunnel. The world had never simultaneously measured unsteady loads on a rotor blade and simultaneously observed that rotor blade cutting through a vortex, and with acoustic arrays in the aeronautics facility measuring the distribution of that noise. And that gentleman is Jim Hubbard, who's with us today. Now, I can't emphasize how strong of a contribution that was. Remember now, this is in the 70s and 80s. How do you get an unsteady pressure signal, the loads on the blades, from the rotating system into the laboratory frame? All we had was gold leaf slip rings. I mean, that's a remarkable achievement. Remarkable. And to build the system itself, to insert the Coolite transducers into the rotor blades, measured in real time while the blade is slashing through the vortex, knowing from our optics that you can see it, and then getting the signal out, that is the loads on the blade, and from the acoustic array, the directivity of the sound. That was outstanding. So, and there's a whole host of students, as you can see on the bottom there, Albert Lee, Alva Mouton, Humbard, Hubbard, Martinez, Layton, Williams, and Scott. Probably some more that should be there as well. But these were the good people. So good they didn't want to move. All right, next is transonics. Okay, so transonics. It's been around since we can remember. There was a time in the development of computational fluid dynamics when we did not know how to capture numerically a shock wave. And there were some leading researchers in the actual development of CFD tools, and they made advances. And they also introduced to us in aero and fluids new kinds of concepts. Numerical instabilities, yes. But for me, there was some unrealism about that. So I asked a bunch of outstanding young people to take on this problem of nonlinear, unsteady transonics. Small perturbations, but still a nonlinear problem. I wanted to come forth with a design tool where I could manage in the analytics, the unsteadiness, the movement of the shock wave on the surface. I wanted to be able to capture the unsteadiness and the actual heaving of the airfoil. And I wanted to do this through a range of Mach numbers. So we developed a set of analytical tools supplemented by existing CFD methods, but integral equations, spectral methods, parametric differentiation being the lead pieces in terms of the analysis. And we were able to extend some of the frequency calculations that at that time remained unresolved. And we have, again, a lineup of students: Cervernini, Sharp, Whitlow, Holt, Lamar, Hanley, Maviferous, Zavadil, Nico Van Kirk, and Dale Carson. Most of those are members of the AIAA. All right, then I lose my way and go to blood flows. So two things happened to me. I was at Duke University on an assignment with a committee, and walking with Professor Lightfoot from Wisconsin, we had a conversation on the onset of crisis in diabetics, people who have suffered from diabetes, which Professor Lightfoot does. And he says, Wes, I am certain that the onset of crisis in diabetes is a chaotic event, not a random event. I then had an opportunity to be on the beach in Galveston with a relative, a young preteen sickle cell impacted youngster. And she ran all during the summer day, staying with me, and never went into crisis. So I asked myself, is the onset of crisis in sickle cell a random event or a chaotic event? And why is that important? If it's random, all bets are off in terms of making any sense of it. If it's chaotic, then there are patterns. Patterns are most likely controlled by physiology of the patient, which means we can go to the pharmaceutical companies to control it. This is just a crisis, folks. But we had to better understand the plasma, blood cells, oxygen diffusion, and how the cells actually change shape. And there are some photos there of normal cells and sickle cells for you to get a visual appreciation of what we were trying to do. So let me deal with this problem, then I'll come back to the sickle cell problem. What happens if you're in a car accident and one of your arteries is severed? Let's say you have a serious impact on the thigh, and that deep in the thigh there's that artery. Most likely, if you aren't treated very quickly, you're going to die from shock. And if you are in the hands of surgeons and first responders, most likely you're going to get your muscles and tendons all ripped in order to get to that artery. So we ask ourselves, how can we stop hemorrhaging without destroying the leg? What we did was actually built in the laboratory a fluid that has the stress-strain properties of blood, human blood. We added to that plasma, micro-sized iron particles. We injected that substance, the iron particles, within that fluid, upstream of the severed artery. We clamp magnets around the area that's impacted The magnet attracts the iron particles and forms a gate and stops the hemorrhaging. Okay, we tried this on rats at Mass General Hospital, and we were able to stop the hemorrhaging, laboratory-induced. We examined the heart, lungs, and brain of the rats to see if there was any deposit of the iron particles. No destruction at all. So now we need to go further and try this on larger animals, in particular pigs. All right, the sickle cell business. Piece I said I'll come back to. So why does sickle cell crisis hurt? Why is it painful? Why does it destroy brain tissue, lung tissue, kidney tissue? The blood does many useful things. It carries oxygen from the lungs to the rest of the body. And that oxygen keeps the nerves well stocked. You don't have the stress. In a sickle cell case, the red blood cells become C-shaped, very brittle, and they do not carry with them oxygen. Second, they actually clog the smaller arteries, the smaller vessels, the veins. So there's no oxygen being transported to a given area, like the elbow, for example. There's no diffusion, therefore, of oxygen from the plasma, or through the plasma, to the surrounding tissue. The nerves are impacted, and therefore, the great pain. So we developed the first and only, as far as I can determine, set of a model that has the physics of the plasma, physics of the actual deformation of the blood cell, physics of the transport of oxygen across the cell of the red blood cells, and the diffusion of the oxygen into the surrounding tissue. Okay, that was very simple, actually. That says nothing about randomness or chaotic features of the onset of crisis. So, we haven't solved the problem. We know what we have to do is somehow, maybe in a reduced order model, transform that set of equations, that physics, into a Lorentz form, and maybe come up with some concrete answers. All right, so now the home stretch. We're into hypersonics. I have a group of students that's working on aerothermodynamics, not materials, not controls, not propulsion, but aerothermodynamics. And some of the problems that the young people are writing their thesis on are identified in this chart. Now, one student is looking at using liquid metals to cool the surface of hypersonic vehicles, to better control the shockwave interaction over hot bodies. Thermally, really hot, hypersonically hot. My passion at the moment is to continue to chase electrons. What Kevin Sabot did was to demonstrate that he could use ions coming from sulfur hexafluoride being heated in a hypersonic stream to use those ions, I-O-N-S, to eat up electrons over a sensor, freeing up S-band communication channels. And that's no big thing. A bigger challenge, chase is to identify the properties of plasma wakes behind ballistics. My prediction, if we can find electrons, we can eat them, we can eliminate them. But what does that mean if you eat up the electrons and a wake? That means you can't see them. You can't see the wake. You can't see the vehicle. You can't see what's coming at you. Who gets to that game first has a distinct advantage, a distinct advantage. Now, do any of you know how or where the electrons are in the wake? That's what I need. So that's the question. The other groups, there's ventilator stability, real gas effects. We have one student looking at plasma-assisted combustion, shockwave structure, etc. And these are our top guns. Notice we started off with Bienkowski. But these are a lineup of the students through the years that I've been able to work with, including this last set on this page. So, my get-off chart. This WALS, this walk through Mach number, Reynolds number, Knudsen number, real gas effects, internal flows, external flows. This WALS is very, very rewarding for me. It has been made possible only because of people. Navier-Stokes was important, sure. Kroko was important, but the real, live, breathing people, the graduate students, my mentors, have played a critical role and made a substantial difference. I cannot overemphasize the power of mentorship. More powerful than the actual problem that you're solving. What you do as a mentor, what you do with the two of you, mentor and mentee, it lasts forever. It just doesn't go away. And that's a prize. Hard, tough questions, technical questions, go for it. Don't go for the low-hanging fruit. Go for the good stuff. Stay abreast of the technology in terms of tools. I'm not very fond of developing tools. I like to use them, but maybe one day I'll learn how to develop tools as well. Stay in your lane. I'm just a disciple of Navier-Stokes. I don't try to do anything else. I think with the Navier-Stokes and boundary conditions, I feel comfortable. Find value in what you do. If we can mitigate crisis in sickle cell, African Americans, Arabs, those along the equator in the southern hemisphere as well, all suffer from sickle cell anemia. They're all blessed in that they are protected from malaria, but sickle cell is it's an exchange. Nature says, okay, I'll protect you from malaria, but I'll give you sickle cell. And that's a part of the game that we have to live with. But find value, do things that are important, and relax and have fun. Thank you.
Thank you very much, sir.
Thank you.
All right, what a great presentation from Dr. Harris, who has, of course, 50 years to look through this, has had several things to study. It was very good. It is my honor and pleasure, Wes, to award you the Durand Medal. Thank you so much.
Thank you, Matt. Thank you, Chris.
And his certificate.
Thank you.
Thank you very much. Let's step over here and we'll get a picture. All right, very good. Thank you. All right, very good.
Okay, thank you.
I think we might have time for one question or two, if you don't mind.
Sure.
So, was there anything in your early history that really just hooked you? What piece of science, what question brought you into the pursuit of answers?
Chris, my response is this. It was Eloise Bowes Washington, my high school physics teacher, who slapped me and to realize how important scholarship is, and the experience of actually building a cloud chamber, as I said earlier, to investigate the collision of alpha particles with water droplets. That was the beginning, that was the foundation, that was the start.
So, what's your prediction for the next 50 years of fluid mechanics research? What do you think is the real challenge and the solutions your graduate students are going to find?
Okay, in the near term, I think there are some real challenges with urban air mobility, especially in terms of the noise field that's generated by the various configurations and energy requirements for urban air mobility, the batteries, if you're going to go electric in particular. Even more difficult, more challenging is hypersonics. All pillars of hypersonics, not just aerothermodynamics, but the materials component. And the awfully challenging guidance, navigation, and control part of hypersonics, the energetics. They're all there, they're all very important. Third, or maybe on top of all of that, is are we going to be able to generate enough scholars, engineers, researchers, scientists to keep us alive and active and well in this field? And to do so with respect for the environment, I think that's a big challenge.
Yeah, very much. So I do have one question that's it's a really personal question. And I think it's one that you have talked about a lot, and it's about mentoring. Key people like Leon Trilling, who mentored you, and those that you've mentored. What is the real role of a mentor, and how have they impacted your career?
Okay. I've tried to approach the opportunity to work with young people by establishing a relationship where if I am ill, the mentee is ill. If the mentee is ill, I'm ill. That bond is strong. If there are any deficiencies on either side, it infects the other. And only by working together are those deficiencies reduced or eliminated, hopefully eliminated. It is based on respect and trust. It is based on respect and trust that must come from the mentor and from the mentee. It may take time to do that, but there's genuine respect and trust between the two parties.
Very good. Thank you again. And let's give a big hand to Dr. Harris. Thank you very much.
Thanks, man.
We hope you've enjoyed the Durand Lecture for Public Service. We look forward to next year's lecture. In the meantime, get out and enjoy the rest of SciTech 2023. Thank you very much. You're dismissed.